Hello, my name is Samin Jamalabadi. I'm presenting our paper on commitment and Slack for online load maximization. Let's start with deadline scheduling. Why is it important? In a real life, there are always some jobs that are only useful if they're executed up to a certain time. For example, it's only useful if you forecast the weather for tomorrow today and not tomorrow. We don't have to address deadline scheduling if we have many backup resources to start each job immediately. For example, it's not an issue for cloud providers like Google or Amazon with plenty of resources, but it's very important for medium-scale cloud providers with limited available resources. Unfortunately, limited resources also may lead to the rejection of some requests. In cloud computing, the price for a resource depends on the amount of time that we lease the resource. Therefore, we want to maximize the load on the machines. We use the common parameter unit penalty uj to express the load. Our problem is an online problem and we use competitive analysis for performance evaluation. In case of maximization, we determine the competitive ratio between the optimal load and the load obtained by our online algorithm. If possibly facing rejection of a request, then the customer wants to know immediately whether the request has been accepted or not and when it will start. The requirement to decide before seeing any other job called immediate commitment. There are also other forms of commitment that have received plenty of interest recently. We can interpret immediate commitment as a contractual agreement between customer and provider. However, the competitive ratio is unbounded for our online problem. Let's see that in an example. A customer submits a small job with a large deadline at time 0. To prevent an infinite competitive ratio, we have to accept this job and start it at some time t. Here at time 0. Then another customer submits an arbitrarily large job with a tight deadline at this time t. We cannot accept the second job. How can we prevent that? By allowing a slack. A slack relates the processing time of a job with its deadline. Consider a job with processing time of 2. In the figure, you see a slack of 2, 1, 0.5 or 0. A larger slack value leads to a larger deadline and gives a job a better chance to be accepted. Therefore, a slack represents a scheduling flexibility. Now you can see our problem in common three-field notation. We consider the parallel machine environments with three constraints of online slack and immediate commitment in order to maximize the load. The indicator variable uj is 1 if and only if we reject job jj. We introduce the handling of the problem by considering the well-known results for a single machine and assume that the slack value is less than 1, although the results hold for all positive slack values. At time 0, the adversary submits a base job with a unit processing time and a large deadline. The algorithm must accept J1 to prevent an infinite competitive ratio. It starts J1 at some time t. For this example, we assume that t is greater or equal than 1. Therefore, the optimal schedule starts J1 at time 0 and completes it at time 1. Then at time t, the adversary submits job J2 with a slightly smaller processing time than job J1 and a tight deadline. Job 2 must start before time t plus 1 to be finished on time. Therefore, the online algorithm cannot accept the second job. The optimal schedule starts job J2 at time t. Then, the adversary submits the third job at time t with a tight deadline. The adversary has selected the processing time of job J3 such that it can be executed immediately after job J2 but not after job J1. Therefore, the algorithm must reject this job as well. An optimal schedule executes job J3 after the completion time of job J2. Determining the ratio of the load of the both schedules yields the competitive factor. Goldwasser shows that the competitive ratio of the simple greedy acceptance approach matches this lower bound. Here you can see our results. The function of the competitive ratio over the slack for different values of m. We're looking at the slack values between 0 to 1 due to a practical and a theoretical importance. In practice, system providers want their system to be used for urgent jobs, meaning a small slack value. Also in theory, the competitive ratio is relatively small for slack values larger than 1. The competitive ratio depends on the slack epsilon. You can see different functions for different numbers of machines m. The functions are continuous but not smooth. The function for m machines has m intervals. The borders of these intervals are marked with a small red circle. Let's consider this problem here for 3 machines with a fixed slack value in the second interval and find the lower bound. At time 0, the adversary submits job J1 with processing time 1 and a very large deadline. The algorithm accepts job J1 and starts it at time t. For this example, we assume that t is greater or equal than 1. Therefore, the optimal schedule starts J1 at time 0 and completes it at time 1. Then, at time t, the adversary submits up to 6 identical jobs J21 with processing time slightly less than 1 and a deadline that allows a machine to execute exactly 2 jobs J21. We assume that the online algorithm accepts the first job J21 and starts it at time t on machine M2. Note that the adversary has selected the processing time of job J21 such that the algorithm cannot allocate it to machine M1. Then the adversary stops submission of jobs J21 and submits up to 6 jobs of J22. The conditions for job J22 are similar than those of J21. In particular, we cannot execute J22 on any machine that already executes another job. The algorithm rejects all, although machine M3 is still idle. The optimal schedule can start 2 copies of job J22 on each machine at time t. Then, the adversary submits up to 3 jobs J32 at time t. The adversary carefully selects the processing time of J32 and its deadline, such that we can execute 1 job J22 and 1 job J32 on the same machine, while it's not possible to execute job J32 together with either job J1 or job J21. The algorithm accepts the first job of J32 and allocates it to machine M3. Finally, the adversary submits up to 3 jobs J33 satisfying similar conditions as job J32. In particular, the algorithm cannot execute job J33 on a machine with any other accepted job. Therefore, the algorithm must reject them all. However, the optimal schedule can execute one of these jobs together with 1 job J22 on every machine. Note that in the second interval, we only accept 2 jobs with processing time close to 1. In this slide, you can see the whole game between the adversary and the online algorithm as a game tree for 3 machines and interval 2. The construction of lower bound consists of 3 phases. In the first phase, the adversary submits the single job with processing time of 1. The online algorithm must accept the job to prevent an arbitrarily large competitive factor. As already mentioned, every job in the second phase has a processing time slightly less than 1 and a deadline that is t plus twice its processing time. The adversary selects the processing time such that the online algorithm cannot execute any two accepted jobs on the same machine. As soon as the online algorithm has accepted a job, the adversary submits the next job with a slightly different processing time. If the algorithm has rejected two identical jobs, here 6 jobs, then the adversary either stops submission or continues with the third phase depending on the number of accepted jobs. Again, the algorithm cannot execute any two accepted jobs on the same machine, while the optimal schedule allocates one of the last rejected jobs of the second phase and one of the last rejected jobs of the third phase to each machine. As an instance, we represent a path marked in red, which ends in two branches of red and green. For the green path, the Gantt chart shows the online schedule and the optimal schedule. Then we obtain the displayed competitive ratio. We have already discussed the red path in some detail. Here you see the Gantt chart in comparison and the resulting competitive ratio. The adversary wants to prevent us from picking the best solution and makes both equal, which results in a key recursion. Note that the F values are the processing time of a job plus 1. Therefore, they are always greater or equal than 2. And the last parameter, which is here F3, always has the value of 1 plus 1 over epsilon. Note that this value is always at least 2 in our range of epsilon. Now, let's see possible approaches to solve our problem. The old approach uses the greedy acceptance with competitive ratio of 2 plus 1 over epsilon for parallel machines. In order to be better than this, we present a new approach for parallel machine that's based on a threshold deadline. Let's see in an example how to determine a threshold on 3 machines. First, we order the machines by decreasing remaining load. Since epsilon belongs to interval 2, then we use only machine 2 and 3 for determination of the threshold. To this end, we multiply the outstanding load of a machine with the corresponding parameter of the recursion, in addition to the current time, and select the largest machine deadline to be the deadline threshold. Now assume a new job J submitted at time 0 with a deadline smaller than the deadline threshold. The algorithm rejects this job although its processing time is so small and there are valid schedules that allow execution of this job. The algorithm only accepts a new job if its deadline has at least the value of the threshold regardless of the processing time of the job. Therefore, our algorithm accepts this long job. We use best fit to allocate an accepted job to a candidate machine. A machine is a candidate machine for an accepted job if it can complete the job on time after completing all other jobs allocated to it. For example, job J cannot be completed on time on the first and second machine, but it completes on time on the third machine. Note that there is always at least one machine that completes an accepted job on time. The algorithm allocates an accepted job to the candidate machine with the largest outstanding load. Therefore, we allocate job J to machine M3. After updating the load on machine 3, we have to reindex the machines based on decreasing remaining load. The key property of our algorithm is based on the contribution of each accepted job J to a specific interval of the schedule. Let's consider the interval starting at the release date of a newly accepted job and ending at the deadline threshold delete. We continue with our previous example in which the algorithm allocated the accepted job J to machine M3. since it was not possible to complete job J on time on machine M2. Therefore, any valid completion of job J must execute the orange part of this job in interval Rj to dlim. When calculating the competitive ratio, this part does not only appear in our online schedule, but also in the optimal schedule in interval Rj to dlim. Further, it's easy to see that the load on machine M3, including job J, is always larger than the load on machine MK. In our example, it's even larger than the load on machine M1. We go through the concept of our proof in 3 steps. In the first step, we consider a covered interval Ts to Te, such that for each time T in this covered interval, it's possible that there is a rejected job that can execute at time T. In the first step, we consider 2 additional conditions for the covered interval. First, all jobs are released in this interval if they contribute to the interval in the online schedule. Second, as soon as less than k machines are busy, it's not possible that the number of busy machines increases in the rest of the interval. You can see both conditions in the example. All loads start at time Ts or later. For the second condition, we consider the pair of time instances T prime and T double prime. You can see that less than 2 machines are busy at time T prime while no machines is busy at time T double prime. Of course, we can shift T prime and T double prime and the property still holds. Then we use the key property of the algorithm to show that the competitive ratio for this interval matches the lower bound. First, we consider a situation when machine MK determines the largest threshold of this interval threshold. For this situation, we can ignore any load on a machine with an index larger than k. Second, we assume that a machine Mi with I greater than k determines the threshold. For example, here, we added a new job to machine M3 and this job increased Te. Therefore, machine M3 determines the threshold. For the detail of the proof, please take a look at the paper. In the second step, we only require the validity of the release date condition, that is, all jobs contributing to the interval also have a release date in the interval. You see that the schedule in the example does not satisfy the second condition anymore, since there is a time instance with only 1 busy machine, while at a later time instance in the interval, 2 machines are busy. Informally, we can consider this type of interval as a concatenation of several intervals of the previous step. In both steps, we can prove that the competitive ratio for these intervals matches the lower bound. In step 3, we also remove the release date restriction. Here you can see that the load on machine M1 starts before Ts. Consider the 3 colored jobs. Since our online algorithm uses best fit, it's possible that all the colored jobs may be released before time Ts. However, the optimal schedule can execute all these colored jobs before the interval, thus allowing more rejected load to execute in the interval. Informally, these jobs generate more room in the interval. This may increase the competitive ratio. However, note that our lower bound was already considering that the job in phase 1 can be executed before the other jobs of the lower bound example. Considering this property, we can show that the removal of the release date restriction does not change the competitive ratio for the first 3 intervals, while its impact is limited to an additive increase of at most 0.164 for all other intervals. Note that the competitive ratio function for 2 and 3 machines match the lower bound, since These functions only have 2 and 3 intervals respectively. In this paper, we have presented the lower bounds of the competitive ratio for the online load maximization with slack and immediate commitment on parallel identical machines. Note that the function of the lower bound is continuous in the interval from 0 to 1, while it's not smooth at the borders of the intervals. Then, we have shown a simple online algorithm using a deadline threshold and best fit. The competitive ratio of this algorithm matches the lower bound for up to 3 machines and for the first 3 interval for more machines. For other intervals, there is a small additive gap between the competitive ratio and its lower bound. Finally, note that an increasing number of machines leads to better competitive ratios. In particular, the competitive ratio tends to the function ln of 1 over epsilon for very large values of m and very small slack values, while the competitive ratio tends to the function 1 over epsilon for a single machine environment. Thank you for your attention, and please feel free to ask any questions either in the session or by mail.